Hello, I'm Ozan Erdoğan. I'm studying at Altınbaş University. I'm going to go over the oscillator topic today for the project of the communication electronics course. Oscillators play a prominent role in the field of electronics. We know they generate signals from a 5 Hz to several GHz. Modern oscillators use many different circuits and generate such outputs as sinusoidal, square, rectangular, saw-tooth, and trapezoidal wave shapes. These wave shapes serve many useful purposes in the electronic circuits. For example, they are used extensively through the television receiver to reproduce both picture and sound. Uh, Classification of oscillators. Oscillators can be uh, classified into two broad categories according to their output wave shapes: sinusoidal, harmonic, and non-sinusoidal, relaxation part. A practical oscillator circuit consists of a tank circuit, a transistor amplifier, and a feedback circuit. The following circuit diagram shows the arrangement of a particular oscillator. Uh, Transistor amplifier, the output of the output of the tank circuit is connected to the amplifier circuit, so that the oscillations produced by the tank circuit are amplified here. Therefore, the output of these oscillations are increased by the amplifier. Feedback circuit. The function of feedback circuit is to transfer a parts of the output energy to LIC circuits in proper phase. This feedback is positive in oscillators while negative in amplifiers. You can see switch S1 and opening switch S2 open loop again. The Barkhausen criteria. With the knowledge we have till now, we understood that a practical oscillator circuit consists of a tank circuit, a transistor amplifier circuit, and a feedback circuit. So let us now try to brush up the concept of feedback amplifiers to derive the gain of the feedback amplifiers. Principle of feedback amplifier. A feedback amplifier generally consists of two parts. They are a amplifier and a feedback circuit. The feedback circuit usually consists of resistor. The concepts of feedback amplifier can be understood from the following figure below. Uh, Given that A and B are complex number, it provides two different sets of criteria. This one provides and second provides. The first requirement specifies that the signal returned to the input must be of equal amplitude to the input signal, while the second requirement specifics that the feedback must be positive and phase shifted 0 degrees. The oscillation frequency is determined by the second criteria. This one. The oscillation will held if the first criterion is satisfied, but the second one is not, as the input signal will progressively gets weaker as a result of the phase adjustments of the signals returning to the input after many excursions during the cycle. Electrical noise is caused by random voltage fluctuations of very small magnitudes, which are caused by the random movement of electrons in conductors and resistors. The random emission of carriers in transistor and diodes. The phenomenon of random recombination of electrons and holes. Other frequency components can not have their values increased since they don't satisfy the phase gains net phase shifts zero condition. Um, uh, this figure for oscillations to occur, the loop gain must be equal to unity in magnitude, and the feedback must be of the regenerative kinds. Positive feedback phase of AB is either zero or integer multiples of 360 degrees. Certain oscillator circuits. Firstly, OP-amp based RC phase shift oscillator. Operational amplifier RC oscillators are commonly used oscillators as compared to the transistor oscillators. This type of oscillator consists of an OP-amp as amplifier stage and three RC cascaded networks as feedback circuits, as shown in figure below. This OP-amp is operated in inverting mode, and therefore the output signal of the OP-amp is shifted by 180 degrees to the input signal appeared at inverting terminal, and an additional 180 degrees phase shift is provided by the RC feedback network, and hence the condition for obtaining the oscillations. The gain of the amplifier or OP-amp is adjusted with help of RF and R1 resistance to get the required oscillations. The gain is adjusted in such a way that the products of OP-amp gain and gain of feedback network is slightly greater than 1. The above circuit acts as an oscillator as the loop gain is greater than unity if the OP-amp provides the gain greater than 29. The frequency oscillations is determined by this formula. Second, phase shifting RC oscillators using BGT. In this transistorized oscillator, a transistor is used as active elements of the amplifier stage. The figure below shows the RC oscillator circuit with transistor as active elements. The DC operating point in active region of the transistor is established by the resistors R1, R2, RC and RA and the supply voltage VCC. The capacitor CA, the capacitor of A is a bypass capacitor. Um, the three RC sections are taken to be identical, and the resistance in the last section is and the input resistance high of the transistor is added to R. To the net resistance given by the circuit is R. The biasing resistors R1 and R2 are larger, R1 and R2 larger, hence therefore no effect on AC operation of the circuit. Also due to C negligible impedance offered by the RA minus CA combination. It is also no effect on AC operation RA and CA. When the power is given to the circuit, noise voltage starts the oscillations in the circuit. A small base current at the transistor amplifier produce a current which is phase shifted by 180 degrees. When this signal is feedback to the input of the amplifier, it will be again phase shifted by 180 degrees. If the loop gain is equal to unity, then sustained oscillations will be produced. By simplifying the circuit with equivalent AC circuit, we get the frequency of oscillations. This is a formula. Oscillations frequency determined by, and precondition is provided by this formula. Another type, Wien-Bridge oscillator. Wien-Bridge networks are low frequency oscillators which are used to generate audio and sub-audio frequencies ranging between 20 Hz to 20 kHz. Further, they provide stabilized, low distorted sinusoidal outputs over a wide range of frequency, which can be selected using beside resistance boxes. In addition, the oscillation frequency in this kind of circuit can be varied quite easily, as it just needs variation of the capacitors C1 and C2. However, these oscillators require large number of circuit components and can be operated up to a certain maximum frequency only. The formula oscillation frequencies, this formula, the bridge outcomes analysis, and this formula. Another type, oscillators that are not sinusoidal part. This is a non-linear RC relation oscillator using a comparator or an operational amplifier. The circuit is configurable for signal or dual supply operation. Essentially, only voltage levels of the waveform are different in signal and dual power supply modes. Charge and discharge times are the same in signal and dual supply modes. Consequently, the periods or frequency is the same in two modes. When using a comparator, this circuit shown is for push-pull output drivers. For open collector output comparators, a pull-up resistor from the outputs to the positive supply is needed. The pull-up resistor provides the charging paths for the capacitor if differences in timing relative to the circuit shown is to be minimized. The pull-up resistor should be as low as possible. This picture is waveform, non-sinusoidal, and circuit diagram in this picture. High frequency turned oscillators, Hartley oscillator and Colpitts oscillator. These frequency formulas, Hartley oscillator and Colpitts oscillator. I'm talk about firstly Hartley oscillator. Hartley oscillator circuit and working procedure. This circuit diagram of a Hartley oscillator is shown in the below figure. And NPN transistor connects in a common emitter configuration works as the active device in amplifier stage. R1 and R2 are biasing resistors, and RFC is the radio frequency choke which provides the isolation between AC and DC operation. At high frequencies, the reactance value of this choke is very high. Therefore, it can be treated as an open circuit. The reactance is zero for DC condition. Therefore, causes no problem for DC capacitors. The capacitor of E is the emitter bypass capacitor, and resistor of E is also be a biasing resistor. The CC1 and CC2 are the coupling capacitor. When the DC supply is given to the circuit, the collector current starts rising and begins with the charging of the capacitor C. Once the capacitor C is fully charged, it starts discharging through L1 and L2 and again starts charging again. This back and forth voltage waveform is a sine wave which is a small and leads with its negative alteration. It will eventually die out unless it is amplified. The transistor comes into the picture. The sine wave generated by the tank circuit is coupled to the base of the transistor through the capacitor CC1. Since the transistor is configured as a common emitter, it takes the input from tank circuit and inverts it to a standard sine wave with a leading positive alteration. And second, Colpitts oscillator, high frequency oscillator. Let us first take a look at the circuit diagram of a Colpitts oscillator. The resistor R1 and R2 and RA provides necessary bias condition for the circuit. The capacitor E provides AC ground, thereby providing any signal degeneration. This also provides temperature stabilization. And the capacitors C and B are employed to block DC and provide an AC path. The radio frequency choke, RFC, offers very high impedance to high frequency currents, which means it shorts for DC and opens for AC. Therefore, it provides DC load for collector and keeps AC currents out of the DC supply source. Tank circuits Mm, the frequency determining network is a parallel resonant circuit which consists of variable capacitors C1 and C2 along with an inductor L. The junction of C1 and C2 are irritated. The capacitor C1 has its one end connected to base via CC and the other two emitter via CE. The voltage developed across C1 provides the regenerative feedback required for the sustained oscillations. Uh, this circuit operation um, when the collector supply is given a transient current is produced in the oscillatory or tank circuit. The oscillatory current in the tank circuit produce AC voltage across C1 which are applied to the base emitter junction and appear in the amplified form in the collector circuit and supply losses to the tank circuit. If, if terminal 1 is at positive potential with respect to terminal 3 at any instance, then terminal 2 will be at negative potential with respect 3 at that instant because terminal 3 is grounded. Therefore, points 1 and 3 are out of phase by 180 degrees. Um, as the as the CA configured transistor provides 180 degrees phase shift, it makes 360 degrees phase shift between the input and output voltage. Therefore, feedback is properly phased to produce continuous undamped oscillations. Thanks to watching my presentation.